For class today, are we just continuing our discussion from Monday?
Yes, and then we're going to start a new chapter, actually.
Okay.
Okay. Yep. And the stuff with chapter 25 and 26, and I will tell you that much right now, is of tremendous weight when it comes to the exam. In addition to how to calculate the electric field, which is actually the other half of the story. So midterm will rely on this stuff. So take these things extremely seriously, okay? So that is something that I must tell you in here. If you guys have never seen an Arduino board before in the past, this is how it looks like. This is the old Uno. This is my own. And this is a resistor. If you have never worked with they're all color coded. And in the past, we used to, because they don't give you the value of the resistor in here, how much resistance is in there. So you usually have to read the colors and basically decipher the colors. There are two kinds of colors. There is a 4-color and there is a 3-color. And there is actually an additional color to either. And that additional color is for the precision. But nowadays, you don't really need to remember any of the colors. I mean, if you happen to go to work in the electronics departments or something with the military, they require you to remember those things. Now you have apps that do that for you. All you have to do is just plug in the colors and they will tell you exactly what the value of the resistance. And if you're in doubt, all you have to do is just pick a multimeter device and it's going to tell you what that resistance is, because it's important before you plug your devices to have proper protections for them. So I'm trying to look for another resistor in here and I don't see any. I have a lot of diodes, a bunch of diodes, transistors. There is a transistor, by the way. You can tell it's transistor because it has 3 legs. There's a base and it has the other ones. Okay. And I don't see any other thing, guys. For right now, it's okay. Anyway, so this is, I was talking to before the recording, for those of you who just came in late, that there is a project that is going to start soon. And I'm hoping that you guys jump on it involving the STEM Center. So I'm hoping that some of you will sign up on it because it's going to be a NASA project, and hopefully wait for the details. And we're going to get it going so that we're going to present sometime in August our project. Okay, so let's continue the chapter. Any questions of what we did last time?
Not from last time, but Professor, I have an unrelated question. Could I ask you real quick?
Go ahead.
Are you going to provide a study guide for the midterms and finals?
Yeah, here is the deal. Okay, Milo, that's a very good question. Is it Milo who asked it or somebody else? Because I was not looking.
It was Milo.
Okay, very good. Listen, these problems that I'm doing in class with you guys are going to be about 50% of the review for the exam. So come exam time, all of these problems that we are doing right now, you have to go through each and every one of them and know how they are solved. The other half is coming from the homework. Okay, and these problems are not too different from the homework. So these problems actually, a lot of them are inside the homework set. So these problems that we're doing in class, they will actually, if you count them, they're about 75 to 80% the preparation for the exam. Is it good?
So we pretty much would have seen what's on the exam already?
Yes, all of these problems that we're doing in the class, they are actually review for the exam. When I pick a problem, like for example, from chapter 25, we already did problem 71. So I assume that you guys can do that problem or something similar to it. It's not going to be something exactly like it. It's going to be something similar to it, where you should be able to right away solve problems, okay? So this is really the intent of all of these problems I spend in the classroom, and they are 50-50 of the lecture. 50% of the lecture, if you noticed, we've been doing theory, and the other 50% we're doing problems. And I tend to be verbose. I tend to over-explain at times, and it may sound like it's too complicated, but if you go back in it and think about it, it's going to be easy. Now, here is the deal why over-explaining sometimes is really necessary, because sometimes, like a question, why do I have to divide by that number and that number? So when you come back in here and you see that over-explanation, so I'm hoping that to explain it, and it's still, you can still ask questions if it's still not good enough. The only thing that is going to stand away from you and getting a good grade in this class is actually not doing those work. not going back and not relying on the fact that you are the ones who are supposed to do it. Go back through each and every one of those problems and do it yourself. In other words, you have to work out those problems. If you're stuck, you come back to these videos and see how it's done so that you can move along. You have to understand these things. That is the only reason that should prevent you from doing well in this class, is not to do these things. Does this make sense to you, Milo, now?
Yeah, that sounds good. Thank you.
Okay, very good. Anyway, so let's do problem 70 now, because I think problem 70 also has tremendous good ideas that we need to solve. Problem 69 actually is promising, but it's more of a practical problem. The picture doesn't look so standard. I mentioned last time, let me first of all pull my OneNote, and this is chapter 25 problems. Okay, so we did 70 already in this class. So let me share the screen. Do we need to share the whole screen or just the app? I want to just share the app. Okay. So anyway, so let's work out problem 70 for right now. Problem 70, if you notice the following on it. So this is 70. So what you have in here is you have a resistor R1. Since Wednesday next week is a holiday. It's a holiday, it's not? Just to make sure, okay, because I may have had that written in my mind, but probably it's not. It's a holiday, isn't it? Can you guys confirm?
Yeah, I think it's Cesar Chavez Day.
Okay, so we don't have class on that day, but I promise I will give you a link for a discussion on, because I have another class going on also in the same fashion, okay? So I'm going to provide you the link for that class in your class so that if you catch up on the problems that we're going to be doing from chapter 26, because there will be a bunch of them from chapter 26, okay? So this is what this problem is giving you in here. It's giving you a capacitor C1. And it's giving you actually a capacitor C2 also. And this whole thing is connected back to a battery. Okay, and this is basically the side of the battery. When you have this leg, which is longer than the other one, that is the positive side of the battery. Usually the voltage of the battery is written with epsilon. This stands for the EMF, the electromotive force, okay? The voltage on it, how many volts on the battery in here. Batteries, normal batteries have internal resistance, so you have to include that in series with the stuff, as if you have another tiny resistance in here. But for the case that we're most of the time we're going to be dealing with, we're dealing with ideal batteries that don't have any internal resistance whatsoever. So this problem, consider the circuit shown in the figure. The battery has an EMF of 72 volts. So the EMF in here, epsilon, is exactly 72 volts. They'll give you that. And the negligible internal resistance, so we don't care about that. R2 is 2 ohms. So this is 2 ohms. Okay. C1 is 3 microfarads, and C2 is 6 microfarads. Okay. After the capacitors have attained their final charges, that means there is no more current flowing through them. So if you're curious about how much charge is going in here, that is exactly 0. I mean, how much current trying to build up more charges? You can't, because that's the purpose of the current, is to put more charge. But this is fully charged. Now there is no more current. Same thing in here. The current is 0. So whatever current is coming through the battery, of course, going through R1, that current needs to go straight out in here, because there is no current on this side, which is equal to 0, because the sum of these two is 0. So all the current need to go through this resistor and come back to the battery, and now we have this current flowing through this side. It's going clockwise, but that's fine. Okay, so that is basically how the current is circulating in this loop. Okay, so that is basically what they tell us, and then they say that the charge on C1 is Q1 equals to 18 microcoulombs. So this charge is 18 microcoulombs. Okay. So after the dust settles, after you turn on switch, there is a switch somewhere in here that the book is not showing you. Usually it's immediately after or before the battery. So that's when you turn on the switch. Then in this case, there is a buildup of a charge. That's what we're going to study in chapter 26. Once they are fully charged, both of them, that's it. We notice that the charge in here is 18 microcoulombs. Okay. And then they ask you in this case to find what? The final charge on C2. So we need to know Q2, basically, how much is it going to be? And also, they want to know the value of R1 itself. We don't know what R1 is. They didn't give you that. Okay. So here is how to tackle this problem. Since you know the charge in here, since you know the capacitance in here, so you know the voltage between this point and this point. This point is the same point as this point. And that point is the same point as this point. So if I start labeling points in here, let's say, for example, this is point 1. This one is point 2. This one also is point 2. And this one also is point 2. They're the same point. This point now is 3, which is the same point as here, which is the same point in here, which is actually here too. This wire is only one unique wire that is connecting all 3 of them. So in this case, the voltage difference between 2 and 3, V23, according to this capacitor, it's this charge Q1 over C1, and Q1 is 18 microcoulombs divided by 3 microfarads. The micro and the micro cancels, which was one of the remarks that we made last time. Don't convert anything. They may cancel on you before you do any calculation. And that they did in this case. 18 divided by 3 is 6. It's coulomb over farad, that is volt. So this is a 6 volt between 2 and 3. Okay. Since the point 2 and 3 is actually the same thing in here. The reason why 2 and 1 are not the same is because of the fact that I have a resistor in here. There is a voltage drop between this 1 and 2. And actually the voltage difference is R1 times I. That's why the points 2 and 1 are not the same. Actually, the difference between 1 and 2, which if you want to call it V1 minus V2, is exactly R1I. Since R1 is potentially not 0, if it is 0, yeah, 1 and 2 will become the same thing. Between here and here, the wire has no resistance. So that's why the point 2 in here is the same everywhere. Since there is no resistance, if you want to apply it, it's 0 times I. Actually, the current also is 0 in here too, so it doesn't matter. But the current in here is 0. That's why this point is identically the same everywhere. Okay. So the voltage between 2 and 3, on the other hand, which is the same thing, is Q2 over C2. Why? Because C1 and C2 are actually in parallel, as you can clearly see. When they have the same voltage, they are in parallel. That's it. So they have the same voltage, and that is 6 volt. From here, we're going to find Q2 equals to V23 times the capacitance in here, which is C2, and that would be 6 volts times the capacitance, which is 6 microfarads. And the 6 times 6 is 36. So it's 36 microcoulomb. That is basically how much charge is inside that capacitor C2. So that answers this question, which is question A from this problem. The resistance R1 now. For me to find the resistance R1, I really have to know what this current I is. Because I know the voltage in here from 2 to 3 is 6 volt. I just found it. This is 6 volt. Which is the same thing everywhere. I know in here it's 72 volt. 72 is 6 plus something, which must be 66 volts. So there is a 66 volt in here. And that 66 volts in here need to be equal to this resistance times that current. So I need to find that current. So how am I going to find that current is by noting also that R2 is actually also in parallel with C1, which is in parallel with C2. So R2 then, which is V23, it's the same thing as R2 times I. From here, we should be able to get what this I is. So that is 6 volts, the same voltage. Okay. So 6 volts is equal to R2, and R2, they tell you specifically it's 2 ohms. So this is equal to 2 ohms times I, which is 6 volts. And in this case, it's going to give me a current of 2 amps, 3 amps, 2 ohms, and that is 3 amperes. So the current is 3 amps. That is flowing through R1 and R2, through the battery also. So that is the current, which is a lot of current. So let's now study this circuit, the remaining of the circuit. So here is the story. The difference in potential between 1 and 3, okay, is on one hand, you can clearly see that this difference in potential is the EMF of the battery. This point in here is at 72 volts more than this point, and this point is exactly 3, and this point is exactly 1. So on one side, it's 72 volts. And on the other side, it's actually V13, which is actually equal to V1 minus V3 is V1 minus V2 plus V2 minus V1, minus V3, I'm sorry. Does this make sense to you? Here is what I'm saying. The difference in potential between 1 and 3 on this side, it's the difference in potential between 1 and 2 and 2 and 3. Written this way, it's perfectly legit, isn't it? To write it this way, yes or no? Okay, very good. So the difference between V1 and 2, that is V12. So this expression actually can be written as V12 plus V23. V12, so let me write this expression again, 72 volts, is equal to R1 times I plus R2 times I, okay? I really didn't need to calculate this number. It's 6 volt already. I didn't need to find I, but I needed it in here. So this is 6 volts already. This is 3 amps. So what I have 72 minus 6, that's 66 volts. When I move this to the other side, is equal to R1, which I don't know what its value is, times 3 amps. From here, 66 divided by 3 is 22 ohms. So again, R1 is going to be 66 volts divided by 3 amps, and this is 22 ohms. Does this problem make sense to you guys? How we worked out everything backward until we got the answer. Okay. Okay. So this is problem 70. Again, let's summarize what we're saying in here. This looks complicated, but I'm hoping that it is just because I've been explaining things throughout, okay? So basically, they gave you the EMF in here, which is 72 volts. They gave you the values for R2 and for the capacitances C1 and C2. They also tell you specifically that there is a charge in here of an 18 microcoulomb after the current basically stops from flowing through it and through this one too, okay, when it's fully charged. So at that point, we're supposed to find the voltage. We can find the voltage in here, which is the same voltage in here, which is the same voltage in all of these parallel configurations. So these are all in parallel. So the voltage is the same. So meaning that then I can find Q2, because Q2 over 6 microfarads must be 6 too. So I can answer that question. Now they want me to find the resistance R1, but I don't know what the current is, because if I know what the current is, and I know this voltage drop, because this is 6 volts and this is 72 volts, so here there must be 66 volts of drop going from 1 to 2. So if I know what this current is, then all I have to do is divide 66 by that current. So how do I find the current? I know the voltage drop across R2, and that is 6 volts everywhere. And I know that this is a 2 ohm. So 2 times I must be equal to 6 volts, and that gave me a 3 amp current that must also be flowing from R1. From here, we're going to take that 66, which is just the difference between the entire voltage drop between 1 and 3 and this 2 and 3. So that is, I've narrowed it down to 66 volts in here. From here, we're going to find the resistance that makes this work. 66 volts is equal to R1 times 3 amp, okay? So now we have solved the question, the problem. So this 2 resistors also, they don't look like it because there is a junction in here. And that junction will make it in such a way that, hey, this current splits. So there is, this 2 cannot be in series, but they are in this situation after you wait a long, long time because there is no current flowing. This one, it's the same current, and when the same current, it's they are in series. So that is basically, in a nutshell, what this problem is. Make sense to you guys?
It makes sense now. You're not sharing your screen though. If you're,
I'm sorry, you should. Oh man, I hate it when that happened. Okay, it really is terrible. So this is basically the entire derivation that I went through. But if you have the notes open, and I am hoping that you guys have piece of paper and you're actually doing these things while I'm talking. You're not sitting in here and watching me do these things because it's really not going to help you much. So you really have to have a piece of paper in drawing and writing and basically telling me if we're in class, I'm going to see that at work so that you guys do that. When we were in session, what I used to do in this kind of sessions, I actually asked one of you guys to go on the board and start solving, and we solve it together. Unfortunately, we can't do that nowadays. Problem 69, what it's saying is the following. You have 2 cylindrical cans with insulating sides and conducting end caps are filled with water attached to the circuitry shown and used to determine the salinity levels. The cans are identical with radius R equals to 5 centimeter and length L equals to 3 centimeter. The battery supplied potential of 10 volts has a negligible internal, so it's an ideal battery, and is connected to a series with a resistor R is equal to 15 ohms. The left cylinder is filled with pure distilled water, which has infinite resistivity. That means it's an insulator, basically. The right cylinder is filled with the salt water solution. It is known that the resistivity of the salt water solution is determined by the relationship. Rho depends on the inverse of the salinity. How much salt you put in it, the more conductive it's going to be. The less salt in it is going to be, the more resistive it's going to be. So where S is the salinity in parts of thousands per ppt, parts per thousand. Per thousand of whatever, okay? So if you have 1,000, for example, molecules of water, how much salt you put in it. So that's basically how they measure the salinity. And S naught is just a threshold value of 6.3 ppt. The ammeter is just 448 milliamps, which is the salinity of the salt water. So basically they gave the current. So let's plug this thing in here, okay? So let's plot this thing in here. Let's look. We're talking about problem 69, which is we started backward, I guess. This kind of problem. We did 71, 70, now 69. We're backward build. If you guys read the poems of Shel Silverstein. Anyway, so what we have in here, we have a cylindrical shape. The sides are insulating. The bases are not. Okay. Same thing with this container in here. I mean, I drew them probably not exactly the same size, but they have them the same size. And they have a resistance in here of 15 ohms. So this one is 15 ohms. And what else do we need in here? And we have the battery of 10 volts. The EMF in here is 10 volts. And they gave you the radius R, 5 centimeter. So the radius of the cans is R equals to 5 centimeter. So this radius. So it's from the get-go, we know the area. It's pi r squared. Okay. So that is basically what we're given. We're also given L, which is the same L for both of them, as being the length of the section as being 3 centimeter. Okay. So the left cylinder is filled with a pure distilled water, which is, okay, it is known. So we have salt in here. So this is a conductor. This is pure, and it's an insulator. So there is no charges that's going. So the charges, when they come in here, they will pile up. This is a capacitor actually, and this is a regular R. This is another resistor R. That's it. That's the difference between the two. Because once you put salt in the water, it becomes conductive. So you can find its R, and its R is going to be simply equal to rho times the length L divided by the area. And the area and the length are given in here. Rho for this salt is given by S naught over S. So this is S naught over S. The more salinity you have in this one, that's S. S naught is just a constant number, okay? Divided by A. So you have L, you have A, you have S naught, and you don't know what S is. That's the whole purpose, is trying to find what S is, okay? Now what they tell you in here is that there was an M meter somewhere. Hold on, I didn't draw the M meter. There is an M meter in here. This one measures a current, and the current in it, I, is equal to 484 milliamps. Okay, so this device has a current in it throwing. So this is the current that is going through this resistor. So it's this current I plus this 15 ohm. So it must going through this one, and this one is fully charged in this case. It is not, okay. So they tell you the left cylinder acts as a capacitor for its capacitor. How much charge is present on the upper plates? Note that the pure water has, okay, we have a dielectric relative to this one, so we cannot usually reuse that expression for the capacitance, because we need the capacitance of this, because this is a capacitor. And if you guys remember, C is equal to epsilon naught times the relative capacitance, epsilon R, times the area divided by the distance in this case, which is L, okay? So we have epsilon R for the water. They tell you it's equal, for pure water is 80.4. So we have the capacitance, epsilon naught, the area we have, L we have. So we have all of the data that is needed to find the capacitance C. So what we're saying in here is the current flows through here and comes through here and goes through there. This is similar to problem 70, actually. 71, I'm sorry. Is there a delay in the sound, or is it working fine right now? Because it looks like the internet may be acting up. You guys hear me well? Okay, very good. So we need to find this equation. So basically what I have in here, I have epsilon is equal to 15 times I plus this resistance, which is S naught divided by S times L divided by A. The whole thing is times the current I. I have the current I have L, I have A, I have S naught. I don't know what S is. We have the current again is 0.484 amps. We have the resistance, and this is 10 volts. All we have to do is multiply everything in here, and from here we're going to find the salinity. And it's going to be proportional to S naught. So the units for it are going to be PPT, per parts per thousand, okay? So that's going to tell you what salinity is there. So you were able to actually measure the salinity of a specific solution of water. So that is basically one way of measuring it, okay? And then in order to check the other one, tells you to find the charge on the other one. The voltage now across this resistor must be the voltage in here. And this voltage is Q over C. Since you already have C, you should be able to find what Q is. Q is going to be this C times this voltage, and this voltage simply is going to be 10 minus 15 times I. So the voltage in here between this point and this point, which is the same across both capacitor, both the resistor and the capacitor. This one is acting as a capacitor, this one is acting as a resistor. So it's going to be just 10 minus 15 times 0.484. Okay? What is 10 minus? It has to be a positive number, because if it's not a positive number, we have a disaster before us. 10 minus 15 times 0.484. Yeah, it's 2.74 volts. So the voltage in here and here is 2.74 volts, according to my calculator. And this must be equal to Q divided by C. So all I have to do is multiply this number by 2.74 volts, and I've got the expression for the charge in here. And it's going to be a tiny number. Remember, A is pi r squared, L is 3 centimeters, so the centimeter squared and the centimeter will cancel, but you still have a centimeter squared. This number is too tiny. Epsilon naught is so small, 10 to the negative 12. Although you're multiplying by 80, it's still a very, very small number. So the capacitance is small, so it's going to be either a nanocoulomb or probably a picocoulomb. There's going to be a very small charge deposited on the top of the can. Does this problem make sense to you? I know I didn't do the whole algebra, but I'm hoping that you guys understand how to tackle this kind of problems. Yes? Very good. How about the others? I know we have quite a few people in here. How about the others? What do you guys feel? Elizabeth is good. That's good. Okay. Okay, very good, Jason. Thank you, guys. Okay. So I think we did enough from this chapter, honestly, because it's going. You will see chapter 26, and this chapter will make far better sense for you guys, because chapter 26 is really the culmination of these things. It's really the where we put everything together, because we're going to deal with the capacitor. We did already the resistance, if you wish, in parallel and also series. So we're going to get into, first of all, something called the KCL. The engineers, they like to use the word KCL. Okay, not all engineers though. Those who work in the electrical engineering field, they seem to use this word more often than anybody else. Physicists call them actually Kurkhoff's rules, or Kirchhoff's rules, however you want to call them. They're not really laws, because both of them, there are actually two of them, 1 and 2. Okay, both of them are actually derived from very important laws. One of them has to do with the conservation charge, and we already used that word extensively up to this point. And the other one has to do with the conservation of energy, and we have used that one too. So both of them, we have used them for simple circuits so far without calling them into laws or rules. KCL, by the way, people in electricity, sometimes they refer to as Kirchhoff's circuit laws. Okay, so that's what they refer to when they talk about that. Okay, we're going to call them Kirchhoff's rules because that's how I learned them. And that's how I think the book also calls them this way too, okay? So here is what the rules are. The first one has to do with the junction rule. And this is the item that I want you to really remember from the discussion today, is to put them in your own words, because I'm sorry. Again, you need to really catch me before. When you see me looking on the other side screen, that means that I'm not looking at you. You guys are here. So when I'm talking to here, I'm talking to you. If you see me like this, that means I'm actually looking at the other screen. I'm supposed to share it with you guys. So anyway, so Kirchhoff's rules, the first rule is called the junction rule. So think of it this way, that you have somehow a junction in here where you have more than 2 wires meeting. If it's only 1 wire, it's not a junction. So in this case, I have 3 wires, okay? If you have more than that, that's fine, it's still applicable. So any time you connect more than 2 wires, it's a junction. So in this junction, you could have a bunch of currents that come in and a bunch of currents that leave, okay? So this, I'm gonna put them as positive. This, I'm gonna put them as negative. If you don't like that, if you wanna flip the signs, that's fine. If they're coming, put them negative, and they're leaving, they're positive, as long as you stick to a convention, as long as you don't put them all positive, okay? Everything is coming in here in terms of charges, I'm calling it positive, it's coming, okay? Anything that is leaving, I'm gonna call it basically negative. So I'm gonna start labeling. This one, I1. This one is I2. This one is I3. This one is I4, and this one is I5. The reason why I have 5 in here is because I have 5 actually, five branches from this node. So this is actually called a branch. Each one of them is a branch, okay? Obviously, from my convention, I1 is positive, I2 is negative, I3 is positive, negative, I4 is, let me repeat again. I1 is positive, I2 is negative, I3 is positive, I4 is negative, and I5 is negative, okay? Doesn't matter. Here is what the rule says. The sum of all the i's is 0 because of the conservation of charge. If you have somehow 10 coulomb come one side and another 5 coulomb come from the other side, somehow 15 coulombs came in, of charges per unit time, that's what the current is, 10 amps and 5 amps. That's 10 coulombs for every second that pile up, that comes into that junction, and another 5 coulomb per second that come in from the other junction. And when they meet somewhere in the junction, they must go. They cannot come together. They cannot stay there. There is no accumulation of charges. Charges do not decide, you know what, this is a good place to rest. There is no such a thing, okay? Charges have to be conserved, okay? So at the end, if I count how many coulombs left per second, that's the current basically, then I'm going to find 15. So if they all go on the same branch, that's fine. 15 amps go on the same branch. If they split up, they split up. It doesn't matter. Let's say, for example, 7 went this way, then 8 must have gone to the other side, and that's it. So if 10 come in and 5 comes in, and I have another possibility for them to split, for example, 3 ways. Let's say, for example, I find 8 of them went this way and 3 of them went that way. So the difference, which is 4 in this case, must have gone to the other side, end of the story. So this is basically in a junction. The algebraic sum of all currents for all branches is 0. That is a conservation of charge. Make sense? Good? Very good. So this is stemming from the conservation of charge. The second law, if I have a loop, I have, for example, a device in here, it doesn't matter what that is, okay? I have another device in here, I have another device in here, I have something else in, I could have a battery somewhere or a bunch of batteries, I could have switches, and at the end, switch is probably closed in here. It doesn't matter where I start, pick and choose any points in the loop, any point, okay? Number 1, so you have 2 choices. Number 1, choose a starting point. For practical purposes, usually we start below the battery, usually, okay? You don't have to, but if this is your starting point, that is fine. Now you have to choose a direction. Are you going clockwise or counterclockwise? It doesn't matter, as long as you're going somewhere, okay? If you go clockwise, which is usually the advice that is good if there is only one battery. If there is more than one battery, you really have a problem. Choose a direction, doesn't matter. Choose a random direction. You don't have to stick with one. So in this case, I'm going to choose it to be clockwise. okay? Then the voltage drop from start to finish, where the finish is actually the start point. So this is actually the finish also. The change in voltage is equal to 0. Delta V is equal to 0 on a complete loop. So that's why it's called the loop rule. Why did I say rules in here? Junction rule, loop rule. Okay, those are the two rules. Okay, so you choose a point. It doesn't matter where, honestly. Practice people usually pick up immediately below the battery, especially if there is only one of them. And then choose a direction. Are you going clockwise or counterclockwise? And start following where the voltage drops, like I was doing earlier. I mean, I did this several times before. When you take V1 minus V2, so you call this point, for example, my starting point V1, and then this one is going to be 2, this one is going to be 3, this one is going to be 4, and this one is going to be 1 back again. So what I say in this case, V1 minus V1, which is 0, that's exactly what this expression is saying, actually, must be equal to V1 minus V2 plus V2 minus V3 plus V3 minus V4. Okay, and you get the picture until, so if I have more than that, until at the end I find V somewhere in here minus V1. Of course, I had to have that V something in here with a minus sign. As you can clearly see, algebraically, they cancel. That is exactly what this expression is saying, okay? Here is the trick, though. You have to know how the voltage is actually the sign for it. If I take a resistor, though, and if the current is flowing this way, this is the voltage drop. Okay, this is not an arrow, actually. This is the drop of voltage. In other words, V is positive this way, if I'm moving along with the same direction of the current. But if I happen to hit a place in the opposite direction of the current, let's say, for example, I'm going counterclockwise and the current is going actually clockwise. Or if I happen to do it backward too, if the current actually is going counterclockwise this way, and I'm going it clockwise along this way. So in that case, the voltage drop is going to be negative. So if along I, the voltage drop is positive. Against I, the voltage drop is negative. That means I am going against the current in this case, okay? That is basically how this is expressed. I mean, think about it. The current is like falling down from a higher voltage to a lower voltage, that's all. It's like water, basically. Water flow comes from a higher elevation down to a lower elevation. And that's exactly what you're doing, actually. This whole problem is similar in a sense to elevations. So what you're saying in here, okay, if I go from the first floor to the third floor, I rose 2 floors. If I go from the third floor to the 4th floor, I went only 1 floor up. If I go from the 4th floor to the 11th floor, I went 7 floors up, for example, using an elevator. And then at the end, I went to the 11th floor. From the 11th floor, I come down to the 6th floor. Now I can went down with a negative 6, and then all the way back to the 1st floor. So at the end, I have no change. I'm back into the same floor that I was. So this is similar to keeping track of how high you are when you started from. Obviously, if your starting point for, let's say, for example, is the 5th floor, you go from the 5th floor to the 7th floor, you gain 2 floors. From the 7th floor to the 11th floor, you gain what? 4 floors. And then you go from the 11th floor down to the 1st floor, you lose 11 floors. And then you're going to go back to the 5th floor. You're going to end up with no gain or loss in floors. You're in the same level where you started from. This is the same thing. This is identical. This what's going on in the circuit in terms of voltages is identical to what you do if you're keeping track of how high you are. That's all. Okay. In that case, you're keeping track of actually the electrical, I mean, the gravitational potential energy, MGH, and H is the only thing that changes up and down. And at the end, there is no change in the potential energy. So the only thing that happened in this case, there is no loss or gain in energy. So you had a conservation of energy. This one too is the same thing. Because every V that you change with, every voltage you change with is actually potential energy, Q times V. Instead of mg before, now it's Q. So you're keeping track of the potential energy. So if your starting potential is the same as your ending potential, your starting point on this circuit is the same ending point, then you have gained or lost no potential energy. That's why this one is actually conservation of energy. This is actually the conservation of energy. Okay. We're going to use this. We have a bunch of problems actually for this chapter. I think we're going to spend Monday doing problems. And I know next Wednesday we don't have a class, but I'm going to spend another day with another class on the same problem, more problems. I'm going to share those problems with you, okay? And then if you still have questions about them, please let me know, because we're going to do this one to death using these two rules actually, because you will see not just one loop, you will see a bunch of loops in the circuit, 2, 3, 4, 5 of them, okay? Where the current splits in every junction, every which way, okay? So now you have to keep track of so many variables, so many currents, so many voltages. And you have these rules will come and save the day. If you did any linear algebra, was any one of you lucky enough to take that class, linear algebra? Can answer in the chat if you did. No, nobody. Okay. Well, it's a good class. Okay, somebody did. Good. Okay, if you took linear algebra, you will end up with a matrix basically at the end, with depending on how many loops you have, depending on how many junctions you have, you will end up with a big matrix basically, depending on the unknown variables. And you can use the methods that you guys learned from there to solve for the currents. If you did not learn basically linear algebra, usually the number of problems in here, the number of loops and the number of currents is not high enough for you to even require matrices. However, it helps a lot if you do, especially if you have an exam where you need to calculate the currents. You don't want to entangle and change, because there is a method of substitution. Basically, you calculate one variable in terms of the others, sub it in the remaining of the equations, and then solve for another variable in terms of the others and sub it in the remaining of the equations, and do it until you get at the end one equation with one unknown and you solve for it. And we're going to do that. We're going to do that so that you guys see how that works. Okay. This is prone to mistakes though, because of the fact that the substitutions and change of things in here and there, you might do a mistake. But if you have access to matrices, like a calculator that does matrices, just ask for the determinant. You're going to give you a determinant, which is denominator for all of them. And then once you get the determinant, you can get for the special determinant for each of these currents, and you'll have the answer. So if you know that, that's great. It's going to expedite things. If not, be careful in the calculation, because sometimes it can be too tedious and it needs a lot of focus. So you need to have a lot of coffee next to you so that you don't make a single tiny mistake. It's all algebra, but it's too many, okay, to keep track of. So that is my warning for it, but hopefully we'll do enough to do that. Again, like I said, it's not going to be that complicated circuits in the sense that you don't really need a lot of algebra, but if you did, it's going to help. Okay, so that is my question for that in terms of how to do these things. Okay. Here is the deal though. You will always, using Kirchhoff's rules, you will always end up with more equations than you need. If you apply Kirchhoff's rule for every circuit that you have, you will have some redundancy. You will have more equations than you need, okay? Which is good, because then you can check your answer with the additional constraints, with the additional equations. So that is actually in a sense good, because so in other words, don't write every single equation out there. You will find that, for example, that you will end up with too many equations that you actually need. Once you solve for them, you go for the other one, okay? Because in if there is a node, there is another node that is actually the same node that combines the currents. If one splits the currents, another one will combine them. So there is always one extra node, and there is always one extra loop, okay? There is always one too many equations than you need. because in algebra, in order to solve the system of linear equations with some linear unknowns, with so many unknowns, and this is what they are, you will need at least the same number of equations as the number of nodes, as the number of unknowns. But you will end up, like I said, with more equations than we actually need. So it's basically you will have some left over. Okay. So let's continue now. Since we know Kirchhoff's rules, we're going to use them extensively in this problem sessions, but we still have a couple of items that we really have to address in here. Okay. And those two items are charging a capacitor. And the other one, you probably have guessed it, discharging a capacitor. So how can you put charge in a capacitor? And how is that we can understand it? Of course, I think this is part of the lab too at some time in the future. So this is an RC circuit. So you have a resistor and a capacitor together, and you connect them to a battery. So here is the example. I have actually I need a switch now. So this is my switch. I have a resistor, R. I have a capacitor, C. I have an EMF, E. And they are connected. At T equal to 0, Q is equal to 0. There is no charge in the capacitor. Then at T equal to 0, we throw the switch on. So what's going to happen in this case is charge will start to flow from the resistor and pile up on the capacitor. The capacitor can build up charge over time until at some point, because the voltage starts to grow on it. So initially the voltage is 0 because Q is 0. Okay. So this will act just as a wire, because now as piling up positive charges, it's extracting negative charges from the other side. So it's actually piling up negative charges on the other side, and there's no problem. You can do that. Okay. There is no problem with this process. Here is the deal. As time evolves, Q is no longer going to be 0. There is charge actually that's going to pile up on the capacitor. So the voltage drop in here is not going to stay 0. It's going to start to grow. As it grows, it's going to resist more and more pile up of charges. So the current starts to go down. As the current starts to go down in the circuit, there is less and less putting up of charges until it slows down to a crawl. Actually, it's going to stop. At that point, the charge will be maximum. So it's going to be Q. And this is what we want. How much charge can we put on a capacitor with this circuit? Or how long does it take us to put that charge? Because remember, in all of the problems we have seen so far in here, you wait a long time. How long is long? 1 hour? 3 days? 7 years? How long? We need to know. Do you understand? So in the problems that we've been dealing, whether 71 or 70, they tell you wait until it's fully charged. Okay, I turned on the switch. Now I'm going to look at the watch, and I want to know how long does it take. Okay, so that is a question. So there is a time characteristic in here that I need to find. It's called tau. And this is a lot of problems will deal with that. So this is a time characteristic. Okay, so I need to know what that time is. How long does it take for my circuit? Obviously, it's going to depend on R and C, because R has a say in this whole process. If R is big, it's going to tame the current, and that's the purpose why you need a resistor in there. So the rate at which you're going to pile this thing is not going to really be as much. So the current will be less and less. So because of R there, and so on and so forth. Now it's going to stop and only when the voltage in here will be exactly equal to this one, and that is going to kill the current at all. So there will be no more current in the circuit. So that is how much charge now I have in the capacitor. At least conceptually, this is the idea. So let's see what's going on. I'm going to apply Kurkhoff's rule. I'm going to follow my own advice. So this is my starting point. 1. I'm going to assume that the current is flowing this way. Again, when you're calculating stuff and you don't know where the direction of the current, just give it the direction. If I turn out to be positive, that means good. I chose the correct direction. If I turn out to be negative, that means I should have chosen the other direction. End of story, no problem whatsoever. There is no problem in here at all. So that is really the trick with these problems. So I'm going to choose I coming from the positive node because that's really where it's supposed to come from. It's supposed to come from the battery. So I expect the charges to pile up this way, okay? So Q is going to be positive in here. So Q and I are related to one another as this one. So the rate at which I'm putting charges in here on the capacitor is the current itself. I is equal to dq over dt. Over time, this is how I'm putting charges. Initially, there was no charge, so I'm going to put a current in it to start to putting charges. So Q is going to be positive, and the current should be positive in this direction. So everything should be fine. So again, I'm going to call this point 2. Since I'm going to jump over this capacitor, this is closed now at after t equal to 0. So this whole situation now is some t greater than 0. This is closed, that means, okay? So at that point, this is the point 3. I'm going to jump this capacitor. There is a voltage drop in here of Q over C. The voltage drop in here is Ri, okay? And then once I come back to this point, I am back to point 1. So what I'm saying in here is Kurkhoff's second rule says that V1 minus V1, which is 0, is equal to, first of all, I'm going from the negative to a positive. I'm rising in potential. I'm going up in potential, okay? So I'm going to go from, sorry. Let me write the whole thing, first of all. It's V1 minus V2 plus V2 minus V3 plus V3 minus V1. It's the same thing, okay? Here is what we're saying in here. V1 minus V2 is actually a negative number. Let me tell you why it's a negative number, okay? Because V2 is clearly higher than V1. The potential on the positive side is higher than the potential on the negative side. So this must be negative epsilon. This one, V2 minus V3, the potential in here is higher in here because I'm dropping, I'm following the current in here. So this is actually equal to Ri. Plus, I'm dropping a potential, I'm going from positive to negative now. Unlike in here where I went from negative to positive, I had a negative. Now I'm going from positive to negative, so I'm going to have a positive Q over C. This whole thing must be equal to 0. Does this expression make sense to you guys? Very good. Because I said V1 minus V2, I didn't say V2 minus V1. You have to be very careful in here. And that it has to be V1 minus V1 is equal to 0 because I'm starting, my starting point is my ending point. And actually I didn't mention that, but I'm actually going clockwise, okay? So this is how I'm doing the loop. I'm going from 1 to 2. Since I'm going from low voltage to a high voltage and I'm calculating V1 minus V2, so this must be negative epsilon. This one, I'm going the same direction of the current, so I'm dropping actually in voltage. So 2 and 3, 2 is higher than 3 by Ri. And in here, I'm going from 3 back to 1, and there is nothing except that's capacitor, which I'm dropping from positive to negative, because this is negative Q, by the way, okay? So this is going to be a positive Q over C. So this equation then reads the following, okay? I'm going to move the negative to the other side. It's going to be positive. So it's positive E is equal to Ri plus Q over C. Typically, we write this expression as follows. I is the rate at which the charge is piling up on the capacitor. So I'm going to write it in terms of that expression. So it's going to be R times dQ over dt plus Q over C is equal to epsilon, okay? I have to do some algebraic manipulations in here. I'm going to divide by R and keep the first derivative on one side and move everybody to the other side, okay? So this is what we have in here. We have dq over dt. When I divide by r, I will have an RC in the denominator in here with a q. When I divide by r, I will have an epsilon over r on this side. So it's going to be epsilon over r minus q over RC. So that's basically what this expression is. I'm going to get the common denominator in here because we need it. So it's going to be RC times, what is it? C times epsilon minus q. Since I have dt by itself and dq by itself, and I have a q in here, I'm going to move everything, except that there is another change I'm going to make in here. Okay, hopefully you guys don't mind it. I'm going to write this one as a minus q minus c epsilon over RC. Basically, I took the minus as a common factor in here because I don't like the fact that I have a minus q in here, that's all. So if we write this expression, this is how this looks like. dq over q minus c epsilon is equal to minus dt over RC. Okay, where r and c and epsilon are all constants. Q is not, though. On this side, I'm going to make a change of variable, and the change of the variable is going to be q prime is equal to q minus c epsilon. That means dq prime is equal to dq. This expression then clearly says dq prime over q prime. Does this change of variable make sense to you guys? Because c and epsilon are constants. Okay, very good. So at the end, what we end up with is an expression that looks like this. dq prime over q prime is equal to minus dt over RC. I'm going to integrate both sides. What is the integral of dx over x? If you're sitting in physics for C, we have seen that same integral today. I can't see the chat when I'm sharing. Okay, that's very good. That is actually how it's supposed to be. That is the natural log. Sometimes you probably see the log or something. Please correct it, okay? So it's supposed to be the natural log, okay? Because they are within a constant similar to one another. So this is ln of x, and this is also ln of q prime. I'm sorry, once I integrate, it's not this expression. So this is going to be ln of q prime is equal to the integral of this guy is just minus t over RC plus constant, some constant. That's basically because we're doing integration in here of a indefinite integration. So in this case, q prime, I remind you that q prime is equal to q minus c epsilon. This is how we defined it. So this is actually q minus c epsilon is equal to, when I exponentiate everything, is going to be exponential of negative t over RC time plus a constant. When I do an exponential of a constant, it's going to be another constant. So I'm going to call this constant constant. It's another constant, not necessarily this one. It's the exponential of that constant. It doesn't matter, just another constant, okay? So this is what we're saying in here. Q then, as a function of time, as it's building up in the capacitor, is going to be c epsilon plus some constant times exponential of minus t over RC. I know at t equal to 0, q sub 0 was 0 because there was no charge in the capacitor. This is our starting point. When we turned on the switch, when we closed the switch, at that time there was no charge in the capacitor. We're building it over time to have a big Q somewhere sitting on the capacitor. So this is, we caught it sometime between 0 and infinity, 0 and when the charge is fully charged, okay? When the capacitor is fully charged. So in this case, so, and we know at t equal to 0, this has to be also satisfied. So we calculate q sub 0 is equal to c epsilon, which is just a constant, plus a constant that's coming from the integration, exponential of 0, which is just 1. So that gives me a value, since this is 0, that gives me a value of that constant that must be equal to minus c epsilon. So now we know what that constant is. That is from the initial conditions. These are called the initial conditions. From here, we have q sub t now. We know how this is going to build up in the capacitor. It's going to be c epsilon, that's the same constant, by the way, that is in here and there too, except in there it's going to be with a negative sign, 1 minus exponential of minus t over RC. So this is how the charge is piling up. It's piling up in an exponential fashion. If t goes to infinity, the exponential of the negative infinity is 0. And the final charge is going to be C epsilon, that's all. And the voltage at that time will be C epsilon, which is the charge divided by C, which is just epsilon. As I predicted in here, as we actually thought about it, that's how much charge when we wait, when it's completely, when it stops. The voltage drop in here will be exactly the voltage drop in the EMF. I mean, if you miss the points in here quickly, at t equal to infinity, Q sub t will go to C epsilon minus 0, because this one is just 0. So this is actually the charge that I'm going to put in the capacitor at the end. So Q will be simply C epsilon. So this is the charge at the end. So if you want to know the voltage at that time, voltage at infinity when we wait that long, is going to be simply equal to the charge, which is C epsilon divided by C, and this is actually the EMF. So at the end, when it's fully charged, which is an infinite amount of time, by the way, then in this case, the EMF will be just enough to, the voltage across here will be just in here, so that if I calculate this voltage drop, it's going to be 0. Okay, if you're not sure about the current, all you have to do is find the current. The current from this expression is going to be I, is going to be dq over dt. Obviously, the derivative of the constants in here is 0. And so I'm be left with a minus C epsilon times the derivative with respect to time of the exponential of minus t over RC. Again, this derivative will pull another minus times the minus is going to be a positive, and it will have C epsilon over RC. So the C cancel, and it's going to be basically at the end, I, as a function of time, is going to be positive epsilon over R times the exponential of negative t over RC. In other words, initially when t equal to 0, the current was actually epsilon over R, as if this is just a wire, as if this does not impact whatsoever, as if I only have a resistor with the EMF, and that's exactly what this is saying in here. But that is at t equal to 0. But as t goes on, when t goes to infinity, the exponential dies out and the current drops to 0. So there will be no current across the resistor. So let's plot these two functions that we just found. So this is the story of the charge, first of all, Q as a function of time, and this is time. Initially, there was no charge in here, and it's going to start to grow until it asymptotically reaches this limit, which is Q, and Q is actually equal to C epsilon, and the growth is going to be exponential. Okay? The current, on the other hand, will fall also exponentially. The law that governs it also is an exponential law. If you look at it, it's also an exponential of negative t over RC. So initially, it's an epsilon over R. So this is the current I as a function of time. This is time. And it starts with that finite value starts to come down to 0. So this is how you build the charge in a capacitor. You start with no charge, and you put a charge until it reaches C epsilon, and it's going to be exponential. So when can you say that, okay, I'm good, I have almost what I need? It all depends on this RC. So RC is really the time characteristic that determines how long does it take for you to charge this capacitor. Okay. If R is very small, obviously in this case, the time is very short. If R is very large, the time is very long. So the tau in this case, the time characteristic tau, is exactly RC. So in other words, the exponential of negative t over RC is controlled by this time, negative t over tau. If I wait at tau time, t equal to tau, that means the current will drop by 1 over E, almost 1/3 of what it was before. If I wait 2 taus, it drops by 1 over E squared, which is almost 1/10 of what its value is. So it's tau that is really the one that dictates how long the current charge drops and how long this is going to charge. So the tau is really the time characteristic, and that is its value. So tau is equal to RC. So in all of these calculations that you will see for charging a capacitor and discharging a capacitor, you will need this expression, tau is equal to RC. So typical numbers for tau that we've been dealing with, by the way, if you remember the capacitor of the order of C, let's say, for example, a typical number from the previous problem. Problem 70. One of them was 3 microfarad, the other one was 6 microfarad. So pick a number, it doesn't matter. 6 microfarads. The resistors in that problem itself exactly were of the order of, I'm trying to look at the problem again, I lost it in here. It's 2 ohms. R2 was 2 ohms, albeit that was not the one. So it was the R1 actually that was in series with this guy, 22 ohms. So how much tau, if I really want to build these guys in here, it's going to be 22 times 6 times microseconds, basically. So 6 times 22 is about 130 or something like that, 132 microseconds, not a millisecond, not a thousandth of a second. Okay. So if you wait a second, you have waited a million times this value. So you have 1 over e to the power, what is it? A million or something. What is it? A million or something like that. So this is practically 0. So if you wait a second, it's more than infinity. You guys understand this? So when I say you wait a very long time, for this practical purposes, you wait a fraction of a second and that's it. It's fully charged for these numbers. Okay, so when you're doing this problem, you have to be very careful. I know in here we're putting infinity, t go to infinity, and t go to infinity. How much is the infinity? Probably half a second or maybe 20 seconds or less than that, okay? Fraction of a second, maybe before you even blink your eye, an infinity amount of time has already passed and this charge is already CE, okay? If you really do the measurement and you have an extra precise device, it's 0.99996 digits after that before you start seeing something that is not a 9 in your of C times E, whatever C is. If C happened to be that value of what did I say, about 6, I don't remember, 6 microfarads. 6 microfarads, let's say, for example, we have 72 volts, 72 times this number, so you have that much charge already in the capacitor. You guys have an understanding, and practical understanding. I know the math is sometimes can be convoluted and give you all kinds of things, but at least intuitive in here, that these numbers are very, very, very exaggerated in here. So when I say t equal to infinity, I really don't mean, literally speaking, you have to wait 3,000 years for you to see this capacitor to be fully charged. Make sense? Because tau is just R times C. Does this make sense to you guys? Okay, at least one of you guys will, okay? Please come back to...
Can you just have the t approaches infinity?
Can I do what? Can we go back to the end?
Yeah. Just a little bit further. Just right
there. Okay, let me go back to the expression. Okay, here is how Q sub t that we found it in here, okay? We use the initial conditions to find the charge as a function of time, okay? So when I say t goes to infinity, the exponential goes to 0. Exponential of negative infinity is 0. So Q sub infinity, when t goes to infinity, must be CE minus 0, because this decays to 0 anyways, with an exponential term that goes away. So the charge at the end, when it's fully charged, must be CE, and that's it, okay? If you wait a long time. I throw in some numbers in here to see that that time is really not that long. It's a fraction of a second, fraction of a millisecond, as a matter of fact, to be more specific, okay? So this time is not that long. So before you see this charge in here. So when we took the derivative in here to find the current, because that's the rate at which the current, the charge is piling up on the capacitor, when we take the derivative, it's gonna, if you're careful enough with the manipulation, the signs cancel, and that's very important because you would want current to be positive. The way we chose it is correct, actually, okay? And that makes sense because we're piling up charges. So we cannot pile up charges for doing it in the opposite direction unless we're discharging capacitor, which we will see soon. Okay. Then it makes sense that, hey, we're putting charges in.
Makes sense though.
Okay. So this is the current. And it starts with a finite value, it starts also to decay also to infinity because it has that exponential in it. Because the derivative of a constant, 1 is 0. So the only thing that bothers us in here in terms of constant is this exponential, which is another exponential times the coefficient of the variable in the exponent, which is -1 over RC. Okay? So this is basically how do you build up a chart. Here's the question. And I know we still have about 5 minutes to this. And we have to do the discharge of the capacitor next time when we meet on Monday, okay? We have lab this afternoon. Don't forget that, guys, okay? So at 2 o'clock, we're meeting again, okay? Don't forget that. So let's do this first, and then we will go. Energy. Obviously, after it's fully charged, I know that the energy in the capacitor is going to be Q squared over 2C. And Q squared is C squared epsilon squared over 2C. So this energy, because we found that at the end, this is how much charge we have, C epsilon. So if I plug in the numbers, this is 1/2 of C times epsilon squared. Where did this energy come from? What do you guys think? Where did we get that energy from? Initially, there was no charge in the capacitor. So where did we get that energy at the end of the day? Let's look at the circuit now. Here is the circuit. Initially, we had no charge in here, so we had no energy in the capacitor. After a long time, after an infinite amount of time, the charge became QC. I mean, C epsilon. So when I square it and divide it by C, and 2C actually, I'm going to find 1/2 of C times epsilon squared. So my question here, where did we get that energy from? It must be coming from one of the other guys, doesn't it? So where do we get the energy from? What are the candidates in here for the energy? The candidates are the following: either the resistor, or the switch, or the battery. Which one do you think provides us energy in the circuit?
Battery.
Does that make sense to everybody else also? It must be the battery, doesn't it? Yes? Come on, guys. Okay, at least let's both have people in. So it should be the battery. Let's see if it's really the battery. Okay, how much energy did we get from the battery? Let's check now the story of the battery. Okay. So this is how much energy stored now. The battery now. We know the power that we generate from the battery is just the current times the EMF. That's what we saw last time. So it's really I times the EMF. Okay. And I, we just calculated. Actually, it's equal to epsilon times the, did we have this discussion or not? Because I have a feeling I didn't do it with you guys. For the power. Power is equal to voltage times the current. Did we do that or not? I don't recall.
No, I don't think we did.
Okay, that's very important, okay? Here is the deal. If I have a voltage, V, and I want to move charge against it, so the energy in here, it's just, we talked about it, it's Q times V, okay? But that is if there is a finite energy, a finite charge Q. But what if I just want to move a small amount of charge dQ? So in this case, this is how much energy I'm going to spend for that. All I have to do is divide this one by dt and this one by dt, and the rate at which the energy is being basically dispersed or taken is going to be just du over dt. That is what power is. and dq over dt is just the current. So this is IV. So this is basically the expression that I have in mind. So this is the power in general, okay? It's dq over dt, because dq times v is actually the energy for a unit charge dq, divided by dt, that is actually the current times IV. So this is the expression that I have in mind now, okay? So this is the power. So what I'm saying in here, this is the power that I need to take from, that we took from on a regular rate when the current was running from the battery. So the battery has a fixed EMF, epsilon, and it has an energy, it has a current in it that was running through it when it was charging the capacitor I. So this is the power that is being drained from the battery. It must be at least this number. It cannot be less than that, because if it's the source of the energy in the system. So it must be at least 1/2 of C epsilon squared. Let's see how much it is. The power, I'm going to call it power drained, because we know we stored some already in the capacitor, and this is how much, okay? So it's going to be the sum from 0 to infinity, because this took an infinite amount to charge this capacitor, actually. So it's going to be the EMF times I dt, I of t times dt. And EMF is constant, and I sub t is equal to epsilon. Where is it? Here. It's epsilon over r times that exponential. So let's integrate the exponential and see what's going to have. So it's again going to be epsilon times epsilon is epsilon squared divided by r. The integral from 0 to infinity of an exponential of negative t over rc times dt. I'm going to make a new change of variable in here, okay? I'm going to call t over rc as being x, because you guys like x a lot. So I'm going to find dt from this change of variable to simply be equal to rc times dx. If I make that change of variable, this integral for the power in here, the power that has been drained actually, is equal to epsilon squared over r times rc times the integral from 0 to infinity of exponential of negative x dx. What is the integral of negative x dx? What is the integral of the exponential? Isn't that the exponential itself? Yes? Because the exponential is its own derivative and it's all integral. So the only problem is that negative sign, that's all. So first of all, I have a cancellation, r and r. So this is c epsilon squared, and the integral from, I'm sorry, this is negative exponential of negative x is evaluated between 0 and infinity. At infinity, this is 0. Exponential of negative infinity is 0. So this is 0 minus, so it's going to be plus exponential of 0, which is 1. So this whole integral is just 1 now, really. So this value is actually c epsilon squared. That is how much power drained. Well, as hoped, this is more than 1/2 the inner 1/2 c epsilon squared, the energy stored in the capacitor. This is how much we actually stored in the capacitor. Okay, 1/2 of c epsilon squared. But we drained twice as much. So where did the other half go? So we drained c epsilon squared. This integration gave me c epsilon squared actually. And when I calculated the energy stored in the capacitor, because just it's charge over 2c, charge squared over 2c, it gave me 1/2 of c epsilon squared. Now the question for you guys is, there is a mystery in here. Energy is missing somewhere. We drained c epsilon squared from here and ended up storing only 1/2 of c epsilon squared. And now we have a missing 1/2 of c epsilon squared. Where do you think that went? I know we are exactly at that time, but can you guys give me a guess where that energy might have gone?
Could it be heat?
I'm sorry? What did
Heat?
you say, Jason? Where would that heat go? Which place? Heating what? I mean, the answer is correct. Very good. That is where it's supposed to have gone. So I expect, and this is we're going to resolve this mystery. So we're going to leave it as a mystery. Of missing energy. And this mystery says that somehow 1/2 of c epsilon squared might, at this point, and I agree with you, Not necessarily because we have to prove it, actually. Might have gone to heat the resistor. Okay, once we do that, we are fully in control. If we really indeed prove that, that means we know exactly, we have a full tally of all of the energy where it went, okay? So I'm gonna stop the recording in here because of the fact that we went over time. And we are meeting anyway in a few minutes, okay? So I'm gonna stop sharing, or stop recording now.